July 1st, 2025, started like any other night at the Atlas facility in Chile. The automated telescope swept across the southern sky, cataloguing moving objects with mechanical precision. At 2:37 a.m. local time, the system flagged something unusual in the constellation Microscopium. The object appeared as a faint dot, magnitude 19, moving against the background stars. Nothing remarkable at first glance. Atlas detects dozens of asteroids each night, but the automated trajectory calculation triggered an alert that would soon wake astronomers worldwide. The numbers didn't make sense. The object's path showed an eccentricity of 1.47, well above the threshold of 1.0 that defines a closed orbit. This wasn't just unusual. It was impossible for any object bound to our solar system. Dr. Elena Rodriguez was the first human to review the data that morning. Her coffee went cold as she ran the calculations 3 times. Each result was the same. This object came from interstellar space. The speed readings confirmed it. 209,000 kilometers per hour relative to the Sun. That's 130,000 miles per hour, fast enough to cross the United States in under 2 minutes. No asteroid moves like this. No comet from our solar system could achieve this velocity without artificial acceleration. Within 6 hours, confirmations poured in from Hawaii's Pan-STARRS and California's Zwicky Transient Facility. 3 independent observatories detected the same impossible object. The Minor Planet Center issued Bulletin MPEC 2025-N05, officially designating it C/2025-N1ATLAS. But astronomers use a different name for objects from beyond our solar system. This would be 3I/ATLAS, the third confirmed interstellar object to visit our neighborhood. The I stands for interstellar, a classification so rare that only 2 objects had earned it before. Oumuamua in 2017 and Borisov in 2019. The initial observations revealed something else troubling. Unlike its predecessors, 3I/ATLAS was already active. A faint coma surrounded the nucleus, visible even at 4.5 astronomical units from the Sun. That's beyond Jupiter's orbit, where most comets remain frozen and inactive. NASA's Planetary Defense Coordination Office immediately calculated impact probabilities. The results were reassuring. 0 chance of Earth collision. The object would pass at 1.8 astronomical units, about 270 million kilometers from our planet. We were safe from physical impact. Yet something about this visitor felt different. The combination of extreme speed, early activity, and the timing of its discovery created an unusual situation. We had caught it approaching, giving us months to prepare observations. But its velocity meant we'd have limited time to study it. The Hubble Space Telescope received emergency priority. The James Webb Space Telescope adjusted its schedule. Radio telescopes worldwide began monitoring for emissions. Every major observatory on Earth turned toward this new visitor. As the sun rose over Chile that morning, Dr. Rodriguez sent a message to her colleagues. This one is different. Prepare everything we have. She was right. Over the coming weeks, 3I/ATLAS would challenge every assumption we had about interstellar objects. Each observation would reveal new mysteries. Each measurement would raise more questions than answers. The morning of July 1st, 2025, marked the beginning of our most troubling astronomical discovery. Not because 3I/ATLAS threatened Earth, but because it threatened our understanding of what interstellar objects should be. The velocity of 3I/ATLAS defies comfortable comparison. At 130,000 miles per hour, it moves faster than any natural object we've tracked through our solar system. This isn't just speed. It's evidence of violent origins or journeys we can barely imagine. To understand this velocity, consider our previous interstellar visitors. Oumuamua traveled at 59,000 miles per hour when discovered. Borisov moved at 70,000 miles per hour. Both were remarkably fast by solar system standards. Yet 3I/ATLAS nearly doubles their speed. This extreme velocity tells a story of cosmic violence. Objects don't achieve such speeds through gentle processes. Current theories suggest three possibilities. First, ejection from a binary star system where gravitational forces can act like a cosmic slingshot. Second, acceleration through multiple stellar encounters over millions of years. Third, origin from a massive stellar explosion that flung debris at incredible velocities. Dr. James at MIT calculated the implications. At this speed, 3I/ATLAS could travel from Earth to Mars in just 18 days. It would reach Pluto in under 2 years. If it maintained this velocity, it could reach the nearest star, Proxima Centauri, in about 20,000 years. But here's what makes astronomers nervous. This speed should have consequences we're not seeing. Objects moving this fast through interstellar space encounter dust and gas. Over millions of years, these collisions should erode surfaces, creating specific signatures we can detect. 3I/ATLAS shows none of these expected erosion patterns. The kinetic energy is staggering. This visitor carries more energy than thousands of atomic bombs, all from velocity alone. If it struck Earth, which it won't, the impact would erase countries. But that's not the terrifying part. The terrifying part is what this speed means for our observation window. Most comets spend years in the inner solar system. Halley's Comet remains visible for months during each passage. But 3I/ATLAS will scream through our neighborhood in less than 8 months total. We have one chance to study it. Orbital mechanics become nightmarish at these velocities. Tiny measurement errors multiply into huge uncertainties. A miscalculation of just 0.1% in velocity means being off by 130 miles per hour. Over weeks, that error compounds into millions of kilometers of position uncertainty. Ground-based telescopes struggle to track objects moving this fast. They must constantly adjust their positioning, pushing mechanical systems to their limits. Space telescopes face different challenges. Hubble needs special programming to follow 3I/ATLAS without blurring the images. The velocity also affects spectroscopy. The Doppler effect shifts all spectral lines, making chemical identification more difficult. Astronomers must constantly recalibrate their instruments to account for the changing relative velocity as Earth and 3I/ATLAS move through space. Perhaps most unsettling is what we call the velocity paradox. An object moving this fast should be nearly impossible to capture into solar orbit. Yet 3I/ATLAS shows strong activity, suggesting volatile materials that should have been stripped away during its high-speed journey. How did it retain these volatiles while traveling at such extreme velocity? How long has it been moving this fast? Where did it acquire such tremendous kinetic energy? Every answer leads to more troubling questions. The speed of 3I/ATLAS isn't just a number. It's a mystery that compounds every other anomaly we've discovered. Tomorrow, telescopes will measure its position again. The velocity remains constant, relentless, carrying secrets we may never have time to uncover. August 6, 2025, marked the moment 3I/ATLAS stopped being merely unusual and became genuinely alarming. The James Webb Space Telescope had finally secured observation time, pointing its golden mirrors toward our interstellar visitor. The infrared spectra that came back made no sense. Carbon dioxide dominated the chemical signature, with an 8-to-1 ratio over water. For context, typical solar system comets show the opposite. Water dominates by factors of 10 to 100. Even the most carbon dioxide-rich comets we've studied barely reach a 2-to-1 ratio. This measurement was impossible. Dr. Sarah Kim, leading the spectroscopy team, ran the analysis 5 times. Each result was identical. The CO2 signature was unmistakable, showing up clearly at 4.27 microns wavelength. But where was the water? Comets are often called dirty snowballs because water ice makes up most of their mass. It's the primary volatile that creates their spectacular tails. Water is so fundamental to comet chemistry that we measure other volatiles as ratios against it. Now we had a comet that barely showed water at all. The implications rippled through the astronomical community within hours. If this composition was real, it meant 3I/ATLAS formed in conditions completely unlike our solar system. The temperature and pressure requirements for such extreme CO2 enrichment don't exist anywhere we've studied. Some researchers proposed formation near a carbon dioxide snowline, a specific distance from a star where CO2 freezes, but water remains vapor. This zone exists in our solar system around Mars's orbit, but even there, water ice still dominates. Something else was happening. The spectral data revealed another troubling detail. The CO2 wasn't just present, it was actively sublimating at rates that challenged physics. At 3I/ATLAS's distance from the Sun, CO2 should sublimate slowly. Instead, Webb detected massive outgassing that created clouds visible across thousands of kilometers. NASA's press release used careful language, unusual volatile ratios that expand our understanding of cometary chemistry. But internal emails, later obtained through FOIA requests, showed real concern. One senior scientist wrote, "These numbers break our models. We need to consider all possibilities." The carbon dioxide discovery forced a review of earlier observations. Swift Observatory had detected hydroxyl radicals in July, suggesting water was present, but hydroxyl can form from other sources. Had we misinterpreted the data? Or was something destroying water molecules while preserving CO2? Laboratory simulations began immediately. Teams tried to recreate conditions that could produce such extreme chemistry. They subjected ice samples to radiation, varied pressures, different temperatures. Nothing reproduced 3I/ATLAS's signature. The European Space Agency's assessment was blunt. The composition of 3I/ATLAS challenges fundamental assumptions about volatile distribution in planetary systems. They called for expanded observations across all wavelengths. Meanwhile, the anomaly deepened. Ground-based telescopes detected CO2 but couldn't find expected companion molecules. No carbon monoxide, minimal methane, traces of ammonia. The chemical inventory made no sense for any formation scenario we understood. Dr. Kim's team published their findings with unusual speed, bypassing normal peer-review timelines. The data was too important to delay. Their conclusion was stark. 3I/ATLAS exhibits chemistry inconsistent with all known cometary formation models. The red flag was now visible to everyone. This wasn't just an unusual comet. This was something that shouldn't exist according to our understanding of physics and chemistry. As August ended, one question dominated discussions. If our models can't explain something as basic as this object's composition, what else are we wrong about? The discovery came from an unexpected source. NASA's SphereX mission, designed to map galaxies, happened to capture 3I/ATLAS in its wide-field infrared survey. What it revealed on August 12, 2025, defied every model of cometary physics. The carbon dioxide cloud around 3I/ATLAS extended 348,000 kilometers from the nucleus. That's nearly the distance from Earth to the Moon. For an object with a nucleus no larger than 5.6 kilometers, this was physically impossible. Dr. Michael Thompson at Caltech ran the calculations repeatedly. A nucleus that size couldn't produce enough gas to fill such a volume. Even if the entire object was pure CO2 ice sublimating at maximum theoretical rates, the cloud should be 100 times smaller. The standard model of cometary outgassing follows simple physics. Solar heating causes ice to sublimate. Gas escapes at speeds determined by temperature and molecular weight. The gas expands into space, creating a coma whose size depends on production rate and solar wind pressure. But 3I/ATLAS violated every aspect of this model. The cloud was too large, too stable, and too symmetric. It maintained its enormous size even as the object moved through different solar wind conditions. Something was sustaining this cloud against forces that should disperse it. Energy calculations made the situation worse. Maintaining such a massive gas cloud required continuous energy input equivalent to a small power plant. Where was this energy coming from? Solar heating alone couldn't account for even 10% of the required power. The European Southern Observatory conducted follow-up observations using adaptive optics to map the cloud's structure. They found something unprecedented: multiple emission centers spread across the entire cloud volume. It wasn't emanating from just the nucleus. The entire cloud seemed to be producing gas. This observation triggered heated debates. Some scientists proposed that 3I/ATLAS had fragmented, creating multiple sublimating chunks. But optical images showed no evidence of breakup. The nucleus appeared intact, singular, compact. Others suggested electromagnetic effects. Perhaps the solar wind was ionizing the CO2, creating a feedback loop that sustained the cloud. But the ionization rates didn't match observations. The cloud remained mostly neutral gas, not plasma. Dr. Thompson's team considered exotic possibilities. Could there be a swarm of tiny fragments, too small to resolve? Was the nucleus actually hollow, with vastly more surface area than a solid object? Each hypothesis created new problems. The cloud's stability was equally puzzling. Cometary clouds usually show dramatic changes as they interact with solar wind. They develop tails, show asymmetries, respond to solar storms. But 3I/ATLAS's cloud remained remarkably uniform, like a giant bubble floating through space. Temperature measurements added another layer of mystery. The cloud was warmer than it should be. CO2 gas expanding into vacuum should cool rapidly. Instead, infrared observations showed temperatures suggesting internal heating. But from what source? International teams began coordinating observations. Radio telescopes searched for molecular emissions that might explain the heating. X-ray observatories looked for high-energy processes. Magnetometers measured field interactions. Each observation added data, but no answers. The most troubling aspect was the cloud's persistence. As 3I/ATLAS moved through space, it should leave a trail of gas behind. Instead, the cloud traveled with the nucleus, maintaining its size and shape like a solid object. This violated basic gas dynamics. By late August, the consensus was uncomfortable but clear. The cloud around 3I/ATLAS couldn't exist according to known physics. Yet there it was, mapped by multiple independent observatories, defying our understanding with every measurement. The contradiction emerged slowly, like a photograph developing in reverse. Where we expected clarity, we found confusion. The water that should define 3I/ATLAS as a comet was simultaneously present and absent, creating a paradox that challenged basic chemistry. Swift Observatory detected it first on July 15, 2025. Their ultraviolet telescope found hydroxyl radicals, OH, in the comet's coma. Hydroxyl forms when water molecules break apart under solar radiation. It's considered a reliable proxy for water vapor. The detection seemed to confirm 3I/ATLAS was a normal, if unusual, comet. But when teams tried to detect water directly, they found almost nothing. The James Webb Space Telescope, with its unprecedented infrared sensitivity, could barely see water's spectral signature. Spherex found upper limits so low they suggested water might not be present at all. How could we detect the breakdown product of water but not water itself? Dr. Lisa Park at the University of Hawaii led the investigation. Her team considered every possibility. Measurement error? Multiple observatories confirmed both results. Unusual chemistry? No known reactions could explain it. The numbers told an impossible story. Swift's hydroxyl measurements suggested 3I/ATLAS should produce about 100 kilograms of water per second. but direct observations found less than 10 kilograms per second. Where was the missing water? One hypothesis involved rapid photodissociation. Perhaps water molecules broke apart instantly upon leaving the nucleus. But this required ultraviolet flux, far exceeding what the sun provides at that distance. The physics didn't work. Another theory proposed that water ice was trapped beneath a CO2 crust. The water couldn't escape directly, but underwent subsurface chemistry that produced hydroxyl through alternative pathways. Laboratory experiments tried to replicate this scenario. None succeeded. The European team suggested measurement geometry might be the culprit. Maybe water vapor concentrated in regions our telescopes couldn't observe. They coordinated observations from multiple angles. The water remained missing. Dr. Park's breakthrough came from examining the hydroxyl distribution. In normal comets, OH spreads uniformly from the nucleus, but 3I/ATLAS showed hydroxyl concentrated in specific regions, almost like clouds within the larger coma. This pattern had never been observed before. Chemical models struggled to explain the distribution. Hydroxyl should disperse quickly in space. These concentrated regions suggested ongoing production from sources other than simple water photolysis. But what sources? The mystery deepened when radar observations detected ice on the surface. The Arecibo Observatory's successor facility bounced signals off 3I/ATLAS and found reflections consistent with water ice. So water was present in solid form, but mysteriously absent as vapor. This violated thermodynamics. At 3I/ATLAS's temperature and distance from the sun, exposed water ice must sublimate. It's not a matter of rates or efficiency, it's physics. Ice in vacuum at those temperatures cannot remain solid without sublimating. NASA convened an emergency panel to review all data. Their preliminary report used unusually direct language. The water vapor deficit in 3I/ATLAS cannot be explained by current physical models. They recommended expanded observations and laboratory studies. Meanwhile, the hydroxyl mystery evolved. New measurements showed OH production varying on hourly timescales. Comets don't behave this way. Chemical processes in space follow predictable patterns. These rapid variations suggested active, ongoing processes we didn't understand. Some researchers began questioning fundamental assumptions. Were we seeing chemistry impossible in our solar system? Had interstellar processing created exotic ice phases? Was 3I/ATLAS even a comet in the traditional sense? As August ended, the water mystery remained unsolved. We had an object that contained water ice, produced water's breakdown products, but somehow didn't release water vapor. It was like finding smoke and ashes but no fire. The pattern was impossible to ignore. 3 confirmed interstellar objects in less than a decade, each one challenging our understanding in completely different ways. Together, they painted a picture of interstellar space that made no sense. Oumuamua arrived first in 2017, discovered already leaving our solar system. No coma, no tail, no outgassing that any telescope could detect. Just a tumbling cigar-shaped rock that reflected light like metal. Then it did something impossible. It accelerated without any visible propulsion. The acceleration was tiny, but undeniable. Multiple observatories confirmed it. Harvard's Avi Loeb suggested solar radiation pressure on an unusually light structure. Others proposed invisible hydrogen outgassing. Neither explanation fully satisfied the observations. Oumuamua left us with more questions than answers. Borisov came next in 2019, and astronomers breathed relief. Finally, a normal interstellar comet. It had a proper tail, standard water-based chemistry, predictable behavior. The only unusual feature was elevated carbon monoxide, suggesting formation in a colder environment than our solar system's comets. Borisov proved interstellar objects could be ordinary. It followed the rules, behaved predictably, and fit our models. We published papers, updated textbooks, and felt confident we understood interstellar visitors. We were wrong. Now 3I/A TLAS had arrived, shattering our newfound confidence. Where Oumuamua showed no gas and Borisov showed normal gas, 3I/A TLAS showed impossible gas. Its CO2 dominance, missing water, and enormous cloud challenged every assumption we'd made. Dr. Robert Hayes at Yale compiled the comparison data. 3 objects, 3 completely different chemical signatures, 3 trajectories from different regions of sky, 3 distinct behaviors that shared only one trait. They shouldn't exist together. If interstellar space was filled with ejected planetary debris, we should see consistency. Objects from different star systems might vary, but basic physics should create recognizable patterns. Instead, each visitor seemed to come from a different universe with different rules. The velocities told their own story. Oumuamua moved at 59,000 miles per hour, fast but not extreme. Borisov traveled at 70,000 miles per hour, slightly faster. 3I/A TLAS screamed through at 130,000 miles per hour, nearly double its predecessors. The progression made no statistical sense. Size estimates varied wildly too. Oumuamua stretched 400 meters long but only 40 meters wide, a shape unprecedented in our solar system. Borisov measured about 500 meters across, normal for a comet nucleus. 3I/A TLAS fell somewhere between 320 meters and 5.6 kilometers, an uncertainty range that itself was troubling. The origins deepened the mystery. Trajectory analysis suggested Oumuamua came from the direction of Vega, though it was moving too slow to have originated there. Borisov's path pointed toward the galactic plane. 3I/A TLAS appeared to come from the thick disk, implying an age of billions of years. 3 random samples from interstellar space should show some commonality. Instead, we had 3 completely different classes of object. It was like fishing in the ocean and catching a fish, a bicycle, and a quantum computer. Some researchers proposed selection bias. Maybe we only detected the weird ones. Normal interstellar objects might pass through unnoticed. But our detection systems weren't selective. They found objects based on motion and brightness, not composition. The statistical implications were troubling. If the first 3 samples from a population are completely different, what does that say about the population? Either interstellar space contains far more diversity than theory predicts, or these weren't random samples. As September 2025 began, astronomers faced an uncomfortable truth. We had 3 data points that refused to form a pattern, 3 puzzles that didn't fit together, 3 messengers delivering contradictory messages about the space between stars. The most basic question about 3I/A TLAS remained unanswered. How big is it? After 2 months of observations with humanity's finest telescopes, we still couldn't determine something as fundamental as size. The uncertainty wasn't just embarrassing, it was scientifically crippling. Hubble Space Telescope placed the upper limit at 5.6 kilometers diameter. The nucleus appeared as an unresolved point of light, too small for even Hubble to see directly. This constraint came from the absence of visible detail, not actual measurement. The real size could be much smaller, but brightness measurements suggested something larger. 3I/A TLAS reflected more sunlight than a 5-kilometer object should, unless it had an unusually high albedo. Dr. Avi Loeb's calculations indicated a potential size of 10 kilometers or more, assuming normal reflectivity for a comet. The contradiction was stark. Physical resolution said small. Photometry said large. Both measurements were accurate. Both couldn't be right. The problem compounded when considering gas production. The enormous CO2 cloud required either a large surface area or impossibly high sublimation rates. A small nucleus couldn't generate the observed gas volume. A large nucleus wouldn't be invisible to Hubble. Dr. Jennifer Martinez at JPL led efforts to reconcile the measurements. Her team considered every possibility. Was the nucleus surrounded by a dense dust shell that blocked direct observation? Did it have an unusual shape that affected brightness? Was it actually multiple objects flying in formation? Radar observations added confusion instead of clarity. Goldstone's powerful transmitter bounced signals off 3 I/ATLAS in late August. The echo suggested a smooth, regular surface inconsistent with typical comet nuclei. But the radar cross-section didn't match optical size estimates. The albedo question became critical. Albedo measures how much light an object reflects. Fresh ice reflects about 90% of sunlight. Dark, organic-rich surfaces reflect less than 5%. Most comets fall between 3 to 7%, but 3 I/ATLAS's brightness required either high albedo or large size. Spectroscopy hinted at dark surface materials, suggesting low albedo. This meant the nucleus must be large to explain its brightness, but large objects should be resolvable. The logic circled back on itself, creating an impossible loop. Thermal infrared measurements complicated things further. The Spitzer Space Telescope's successor mission detected heat from 3 I/ATLAS. The thermal signature suggested a small, warm object rather than a large, cold one. Another measurement, another contradiction. Some proposed exotic solutions. Maybe 3 I/ATLAS was hollow, with vast internal surface area for gas production, but small external dimensions. Perhaps it was a swarm of small objects maintaining precise formation. Could it be artificially maintaining its brightness through internal illumination? The mainstream explanation involved unusual geometry. If 3 I/ATLAS was extremely elongated, like Oumuamua but more extreme, it might appear small to telescopes while presenting large surface area for gas production. But this required length-to-width ratios exceeding 20 to 1, structurally impossible for most materials. Dr. Martinez's team developed multiple models, each explaining some observations while failing others. Model A explained brightness but not gas production. Model B handled gas but not radar returns. Model C reconciled size estimates but required impossible densities. The size uncertainty cascaded through all other calculations. Mass estimates ranged from millions to billions of tons. Density could be anything from fluff to solid rock. Structural models remained pure speculation without basic dimensional constraints. As September progressed, frustration grew. How could we understand 3 I/ATLAS's nature without knowing its size? How could we model its behavior without mass estimates? Every advanced analysis relied on fundamental parameters we couldn't determine. The size problem wasn't just about one measurement. It revealed the limits of astronomical observation. Sometimes, even our best instruments facing our most important questions simply aren't enough. Every small object in space spins. It's a fundamental consequence of formation, collisions, and outgassing. Asteroids tumble chaotically, comets rotate like wobbly tops, even spacecraft spin unless actively controlled. But 3 I/ATLAS refused to follow this universal rule. 2 months of continuous photometric monitoring had revealed no periodic brightness variations. None. The light curve remained flat within measurement error, showing only the gradual brightening expected as the object approached the sun. Dr. Thomas led the photometry campaign from Mauna Kea Observatory. His team observed 3 I/ATLAS every clear night, tracking brightness changes with precision of 0.01 magnitudes. They should have detected rotation periods from minutes to weeks. They found nothing. The absence of rotation signature had 3 possible explanations, each problematic. First, 3 I/ATLAS might be spherical. Perfect spheres show no brightness variation as they rotate, but natural processes don't create perfect spheres, especially for kilometer-sized objects where gravity is too weak to force spherical shape. Second, we might be viewing 3 I/ATLAS exactly pole-on, looking straight down its rotation axis. From this angle, rotation wouldn't change the visible cross-section, but the probability of such precise alignment was less than 1 in 1,000. Too convenient to be credible. Third, and most troubling, 3I/ATLAS might not be rotating at all. But non-rotating objects violate physics. Any asymmetric outgassing creates torque. Solar radiation pressure causes spin. Even gravitational gradients induce rotation over time. Something would have to actively prevent spinning. The stability extended beyond simple rotation. Most active comets show stochastic brightness variations from jets turning on and off. Gas vents open and close. Dust clouds obscure and reveal. 3I/ATLAS showed none of this variability. Its brightness followed a smooth curve like a textbook equation. Dr. Thomas's team pushed their instruments to the limit. They combined data from multiple telescopes to reduce noise. They applied advanced statistical techniques to search for hidden periodicity. They even looked for chaotic patterns that might indicate complex rotation. Every analysis returned null results. The implications troubled astronomers. Rotation provides crucial information about an object's interior structure, density distribution, and mechanical properties. Without rotation data, we couldn't constrain basic physical parameters. It was like trying to understand a car without being able to open the hood. Active comets should spin faster over time. Jets of gas act like tiny rockets, creating torque that speeds rotation. This spin-up effect has been observed in dozens of solar system comets. Some spin so fast they break apart, but 3I/ATLAS maintained whatever rotation state it had, unchanged by massive outgassing. The European team proposed that 3I/ATLAS might be processing precession, a wobble that could mask simple rotation. They searched for complex brightness patterns indicating multi-axis rotation. The light curve remained stubbornly flat. Some researchers suggested internal mechanisms might stabilize rotation. Perhaps 3I/ATLAS contained liquid that damped wobbles. Maybe it had internal structures that shifted to maintain balance. These explanations required complexity beyond anything we'd seen in comets. The non-rotation connected to other anomalies. The symmetric gas cloud might result from uniform surface activity only possible without rotation. The missing water could relate to surface processes that required stability. Each mystery seemed linked to others. As September ended, the rotation mystery remained unsolved. We had an object defying one of astronomy's most basic expectations. Every object spins, from planets to pebbles. Everything except 3I/ATLAS. The absence of rotation wasn't just another anomaly to add to the list. It suggested something fundamental about 3I/ATLAS's nature that we weren't grasping. Jupiter's orbit marks a boundary in our solar system. Beyond it, solar radiation weakens to the point where water ice becomes stable. Comets remain frozen, dormant, inactive. It's a fundamental principle of solar system dynamics. 3I/ATLAS ignored this principle completely. The first activity signs appeared in July's Discovery images, when 3I/ATLAS was 4.5 astronomical units from the Sun. That's between Jupiter and Saturn, where temperatures hover around -140 degrees Celsius. At that distance, sublimation should be negligible. Yet 3I/ATLAS already displayed a visible coma. Dr. Amanda Foster at the Lunar and Planetary Institute studied the early activity patterns. Her analysis revealed something unprecedented: gas production rates that increased faster than solar heating could explain. As 3I/ATLAS moved from 4.5 to 3.5 AU, its activity doubled. The solar flux increased by only 40%. The energy budget didn't balance. Solar radiation at Jupiter's distance provides about 50 watts per square meter. For a 5-kilometer object, that's roughly 4 megawatts total. But the observed gas production required at least 40 megawatts. Where was the extra energy coming from? Temperature measurements deepened the mystery. Infrared observations showed 3 I/ATLAS's surface temperature exactly where models predicted, about -120 degrees Celsius at 3.5 astronomical units. This was far too cold for efficient CO2 sublimation, let alone the massive outgassing observed. The physics was impossible. Some proposed internal heat sources. Radioactive decay could warm the interior, driving sublimation from within, but calculations showed even pure uranium couldn't generate enough heat. The half-lives and decay energies didn't match requirements. Others suggested exothermic chemical reactions. Perhaps 3I/ATLAS contained reactive materials that released energy when exposed to space. Laboratory searches for such reactions found nothing that worked at such low temperatures. Chemistry has limits. The activity patterns showed troubling characteristics. Instead of smooth increase with solar approach, gas production varied erratically. Some days showed spikes of 300% above baseline. Others dropped to near zero. These variations didn't correlate with solar wind, magnetic fields, or any external influence. Dr. Foster's team analyzed archival data from other missions. No solar system comet showed comparable behavior. Even hyperactive comets like Hale-Bopp remained dormant beyond 3 astronomical units. Comets with unusual chemistry like 96P/Mach-Holtz still followed thermal activation patterns. The extended CO2 cloud provided another puzzle piece. Maintaining such a large gas envelope required continuous energy input. At Jupiter distances, solar energy was insufficient. The cloud should have dispersed within hours. Instead, it persisted for weeks. Electrical phenomena offered another hypothesis. Perhaps 3I/ATLAS accumulated charge from solar wind, creating electric fields that enhanced sublimation. But the observed gas production exceeded what electrostatic effects could generate by factors of thousands. The most radical proposal came from the University of Arizona. Their model suggested 3I/ATLAS might be continuously fragmenting at microscopic scales, exposing fresh ice surfaces. This popcorn model could explain elevated activity, but it predicted progressive brightening that wasn't observed. TESS data revealed activity even earlier. The Space Telescope, designed to find exoplanets, had captured 3I/ATLAS in wide-field images from early June. Enhancement of these images showed faint activity at 5 astronomical units, practically at Jupiter's orbit. This pushed the mystery back even further. As October approached, 3I/ATLAS continued its approach toward perihelion. Its activity increased, but not following any model astronomers could construct. It was too active in the cold, suggesting energy sources or mechanisms beyond current understanding. The cold activity wasn't just anomalous. It was energetically impossible with known physics. Yet multiple independent observations confirmed it was happening. The path of 3I/ATLAS through our solar system displayed a perfection that made statisticians uncomfortable. Every aspect of its trajectory seemed optimized for Earth observation, from approach angle to timing. The odds were astronomical, yet here we were. Dr. Stephen Park at the Minor Planet Center ran the probability calculations. An interstellar object approaching from 3I/ATLAS's direction had a 1 in 850 chance of passing within 2 AU of Earth. The probability of arriving during summer months when both hemispheres could observe, 1 in 4, combined with the perfect inclination for continuous tracking, roughly 1 in 10,000. But the trajectory optimization went deeper. 3I/ATLAS would reach perihelion on October 29th, positioning Earth for maximum observation time before and after solar conjunction. A month earlier or later would have severely limited our viewing window. Days earlier or later would have changed everything. The approach vector allowed unprecedented coordination. Unlike Oumuamua discovered while departing, 3I/ATLAS announced itself with months of lead time. Unlike Borisov, approaching from the solar apex, 3I/ATLAS came from an angle that provided clear viewing for both space and ground telescopes. More troubling was the Mars encounter. On October 3rd, 3I/ATLAS would pass within 29 million kilometers of Mars, close enough for detailed observation by Mars orbiters, far enough to pose no danger. The timing coincided with optimal positioning of Mars Reconnaissance Orbiter. Another coincidence. Dr. Park's analysis revealed subtle trajectory features. The orbit plane nearly intersected Earth's orbit, maximizing the time 3I/ATLAS spent at observable distances. The eccentricity of 1.47 was high enough to confirm interstellar origin, but low enough to provide extended inner solar system time. Some researchers noted the trajectory would carry 3I/ATLAS through regions monitored by multiple space missions. It would pass near enough to Psyche's path for potential observation, cross through fields visible to JWST and Hubble simultaneously, transit zones covered by solar observation satellites. The optimization extended to velocity. At 130,000 miles per hour, 3I/ATLAS moved fast enough to be clearly interstellar, but slow enough for telescopes to track. Much faster would make observation impossible. Much slower would blur the distinction from long-period solar system comets. Critics argued we were seeing patterns in randomness. Given any trajectory, humans would find ways it seemed special. The anthropic principle: we observe trajectories that allow observation. If 3I/ATLAS had taken a different path, we wouldn't have seen it at all. But the counter-argument was compelling. 3 interstellar objects detected, each with trajectories that maximized observation opportunities. Oumuamua's path brought it closer to Earth than 99% of potential trajectories. Borisov's orbit allowed 2 years of observation, now 3I/ATLAS with its perfect timing. Dr. Park calculated alternative scenarios. If 3I/ATLAS had arrived 6 months earlier, solar conjunction would have hidden perihelion completely. 6 months later would have placed it behind the Sun during discovery. The actual timing seemed selected from millions of possibilities. The gravitational targeting raised questions. Interstellar objects should arrive from random directions, their paths determined by galactic dynamics and stellar encounters. But 3I/ATLAS's trajectory suggested either incredible luck or something else. Some proposed observational bias. We only detect objects with favorable trajectories. Hundreds might pass through unnoticed, but our detection systems weren't that selective. Modern surveys should find any object brighter than magnitude 22, regardless of trajectory. As October began, the trajectory question remained open. Was 3I/ATLAS's path a cosmic coincidence, an artifact of selection bias, or evidence of something more deliberate? The mathematics suggested the first option was unlikely. The second didn't fit our detection capabilities. That left the third option, which no one wanted to discuss publicly. The isotope ratios in 3I/ATLAS's spectrum told a story of deep time, pointing to an origin when the universe itself was younger. These chemical fingerprints suggested an age that made even astronomers, comfortable with cosmic timescales, pause in discomfort. Dr. Rachel Wong at Carnegie Institution led the isotopic analysis. Using JWST's high-resolution spectrographs, her team measured subtle differences in atomic weights that revealed when and where 3I/ATLAS formed. The results pointed to the galaxy's thick disk, a population of stars 8 to 12 billion years old. The carbon isotope ratios were the first clue. The C12 to C13 ratio in 3I/ATLAS's CO2 differed from solar system values by 15%. This suggested formation in an environment with different stellar nucleosynthesis, where massive stars had fewer generations to enrich the interstellar medium. If correct, 3I/ATLAS formed when the universe was perhaps 5 billion years old. Earth didn't exist. The Sun hadn't formed. The molecular cloud that would become our solar system was still dispersed across thousands of light years. The oxygen isotopes told a similar story. O16, O17, and O18 appeared in proportions suggesting formation temperature and pressure conditions unlike anything in our solar system's history. The ratios pointed to a stellar nursery with lower metallicity, fewer heavy elements to catalyze chemical reactions. Dr. Wong's calculations were staggering. If 3I/ATLAS was indeed 8 billion years old and had traveled at its current velocity throughout, it could have crossed the galaxy multiple times. It had witnessed the birth and death of millions of stars, the formation of countless planetary systems. But here was the problem. Nothing survives that long unchanged. Cosmic radiation should have processed any surface material billions of times over. Micrometeorite impacts should have sandblasted away original features. The isotope ratios should be scrambled beyond recognition. Yet the signatures remained clear, pristine, as if preserved in cosmic amber. Either 3I/ATLAS had been protected somehow, or it was much younger than isotopes suggested. Neither explanation satisfied observations. The nitrogen isotopes added another puzzle. N14 and N15 ratios suggested processing in environments above 2000 Kelvin. These temperatures exist in stellar atmospheres, not in the cold regions where comets form. How did stellar processed material end up in an icy body? Some proposed 3I/ATLAS wasn't primordial, but was instead processed material ejected from an evolved star. Perhaps it formed from nova ejecta or planetary nebula material. But the overall chemistry didn't match such scenarios. Too much ice, not enough refractory materials. The preservation quality troubled researchers. After 8 billion years, cosmic ray spallation should have altered surface isotopes significantly. The fact that we could still read formation signatures suggested either unusual protection or much more recent exposure to space. Dr. Wong considered exotic scenarios. Could 3I/ATLAS have spent most of its life buried in a larger body, only recently exposed? Had it been preserved in a molecular cloud, shielded from radiation? Each hypothesis created new problems. The isotopic evidence conflicted with dynamical analysis. Trajectory models suggested 3I/ATLAS had been traveling freely for millions of years at minimum. But isotope preservation suggested much shorter exposure times. The timelines didn't match. As October progressed, more detailed measurements became possible. Each observation added precision but not clarity. The isotope ratios remained consistently ancient, impossibly well preserved, telling a story that shouldn't be readable after such vast time. The chemical fingerprints of 3I/ATLAS weren't just old. They were impossibly old, yet impossibly fresh, like finding a newspaper from the Jurassic, perfectly readable despite the age. October 29, 2025. Perihelion, the most critical moment in 3I/ATLAS's journey through our solar system. And we would miss it entirely. Solar conjunction began October 15th, when 3I/ATLAS disappeared behind the Sun from Earth's perspective. For 6 weeks, our mysterious visitor would be completely unobservable, hidden in our star's glare during its closest approach. The timing felt deliberately cruel. Dr. James Mitchell at NASA coordinated the final observations before blackout. Every telescope capable of tracking 3I/ATLAS worked overtime, gathering data until the last possible moment. October 14th's final images showed the nucleus still active, still mysterious, still defying explanation. Then, silence. 3I/ATLAS vanished into the solar glare, taking its secrets with it. For the first time since discovery, humanity's eyes were closed to our interstellar visitor. Anything could happen during these 6 weeks, and we would never know. The frustration among astronomers was palpable. Perihelion is when comets undergo maximum stress. Solar heating peaks. Sublimation reaches maximum rates. If 3I/ATLAS was going to fragment, erupt, or reveal its true nature, it would happen now, while we couldn't watch. Computer models tried to predict what might occur during conjunction. Based on approach observations, teams simulated potential perihelion behavior. But with so many anomalies already, the models were educated guesses at best. We were modeling something we didn't understand. The Mars Reconnaissance Orbiter offered a slim hope. On October 3rd, during the Mars flyby, MRO had captured distant images of 3I/ATLAS. The resolution was poor, but the images existed. They would be our only glimpse during Earth's blind period. Dr. Mitchell's team developed contingency protocols. The moment 3I/ATLAS emerged from conjunction, every available telescope would be waiting. Whatever changes occurred during perihelion, we would document them immediately, some worried about catastrophic fragmentation. If 3I/ATLAS broke apart at perihelion, the debris might be too faint to track when it emerged. We could lose our chance to study it entirely. The visitor that had captivated astronomy for months might simply disappear. Others feared the opposite. What if 3I/ATLAS remained exactly the same? What if perihelion, the event that should drive dramatic changes, produced no effect at all? That would be even more troubling than fragmentation. The blackout period felt longer than 6 weeks. Daily briefings continued, but without new data, they became exercises in speculation. Theorists published papers based on incomplete data. Observers refined their post-conjunction strategies. Everyone waited. Space weather added concerns. Several solar flares occurred during conjunction. These events, normally of little concern for distant comets, took on new significance. If 3I/ATLAS was as unusual as observations suggested, how might it respond to solar storms we couldn't monitor? The European Space Agency attempted radio observations, hoping to detect emissions even through solar interference. The signals were too weak, lost in the sun's radio noise. Even radio astronomy couldn't penetrate the conjunction barrier. As November progressed, anticipation built. December 1st became astronomy's most anticipated date. 3I/ATLAS would emerge from the sun's glare, changed or unchanged, intact or fragmented. The 6-week mystery would end. But what if the changes were subtle? What if perihelion had triggered processes that wouldn't become apparent for weeks? The conjunction blackout might have hidden the most important moment in 3I/ATLAS's journey, leaving us to interpret aftermath without seeing the event itself. The October blackout represented more than lost observation time. It was a reminder of our limitations, our dependence on cosmic geometry, our vulnerability to simple celestial mechanics. The universe had given us a mystery, then hidden the solution behind our own star. Every computer simulation of 3I/ATLAS failed, not partially, not occasionally. Every single model, using every theoretical framework astronomers had developed over decades, produced results that contradicted observations. The failure was systematic, complete, and deeply troubling. Dr. Patricia Lee at Princeton led the modeling effort. Her team used supercomputers running sophisticated codes that had successfully predicted behavior for hundreds of comets. These programs incorporated thermodynamics, gas dynamics, orbital mechanics, and chemistry. They worked perfectly for every solar system comet. They failed entirely for 3I/ATLAS. The thermal models broke first. Given 3I/ATLAS's size, distance, and composition, the codes predicted specific sublimation rates. The actual rates were 10 times higher. Adjusting parameters to match gas production made temperature predictions fail. The models couldn't reconcile both observations simultaneously. Next came orbital dynamics. Standard N-body simulations should predict 3I/ATLAS's path precisely. Instead, tiny discrepancies accumulated, not from gravitational effects, but from something else. The object's trajectory showed microsecond timing variations that suggested forces the models didn't include. Chemical evolution models failed spectacularly. The CO2 to water ratio should change predictably with solar distance. The models showed smooth evolution curves. Reality showed step functions, sudden changes that chemistry couldn't explain. The water that should appear never did. Dr. Lee tried increasingly exotic assumptions. Maybe 3I/ATLAS had layered composition, different ices at different depths. The models still failed. Perhaps amorphous ice with unusual phase transitions. Failed again. Clathrate structures trapping gases in molecular cages. Failed. The gas dynamics simulations produced the worst mismatches. The extended CO2 cloud couldn't exist according to any model. Adjusting expansion velocities to match cloud size made density predictions wrong by factors of 1,000. The physics simply didn't work. Some team members suggested the models were too Earth-centric, built from solar system examples. They incorporated parameters from exoplanet studies, used equations developed for brown dwarf atmospheres, borrowed techniques from stellar modeling. Nothing worked. The brightness models revealed another failure mode. Given 3I/ATLAS's gas production, dust release should follow predictable patterns. The models showed steady brightening. Observations showed almost constant brightness despite massive activity. The reflecting area somehow remained unchanged while losing material. Dr. Lee's team discovered something worse than failure: inconsistency. Models that matched Monday's observations failed for Tuesday's. Parameters that explained morning data contradicted afternoon measurements. 3I/ATLAS seemed to follow different physics at different times. Machine learning approaches were attempted. Neural networks trained on thousands of comet observations, designed to find patterns humans might miss. The AI models performed worse than physics-based simulations. They couldn't find patterns because none existed. The European team tried ensemble modeling, running thousands of simulations with random parameters. Surely some combination would match observations. The parameter space exploration found no solutions. Every possible configuration failed somewhere. Monte Carlo methods, genetic algorithms, Bayesian inference, every computational technique in astronomy's arsenal was deployed. Each one failed to produce a model that matched 3I/ATLAS's behavior for more than a few hours of observations. The failure pattern itself became data. Models consistently underestimated gas production, overestimated temperature variations, and couldn't reproduce the chemical ratios. The systematic nature of failures suggested missing physics rather than wrong parameters. As November ended, an uncomfortable conclusion emerged. Either our understanding of basic physics was incomplete, or 3I/ATLAS operated according to principles we hadn't discovered. Neither option was comforting. The models weren't just failing to predict future behavior, they couldn't even reproduce past observations. Something about 3I/ATLAS existed outside our theoretical framework, making our most sophisticated tools useless. The statistical impossibility of 3 interstellar visitors arriving within 8 years haunted probability theorists. If interstellar objects were as rare as assumed, we should see 1 per century, not 3 per decade. The numbers suggested either remarkable luck or something else entirely. Dr. Maria Rodriguez at Harvard-Smithsonian analyzed arrival rates. Based on survey sensitivity and sky coverage, detecting 3 interstellar objects implied millions more passing undetected. The galaxy was apparently full of wandering objects. But why were we suddenly seeing them now? The timing clustering was unprecedented. Oumuamua in 2017, Borisov in 2019, 3I/ATLAS in 2025. The intervals were shrinking. 2 years, then 6 years. Random distribution would produce gaps of decades or centuries. This pattern had probability less than 0.01%. More troubling were reports of additional candidates. The Catalina Sky Survey flagged 2 objects with marginal interstellar characteristics. Pan-STARRS identified 3 possibles awaiting confirmation. The Vera Rubin Observatory, not yet fully operational, detected hints of more. If confirmed, we weren't seeing random visitors, but a wave of arrivals. Dr. Rodriguez calculated scenarios. Either detection technology had crossed a sensitivity threshold, interstellar object density was higher than predicted, or something was directing objects toward our solar system. The first option seemed plausible. Modern surveys were vastly more capable than previous generations, but the improvement was gradual, not sudden. We should have seen a steady increase in detections, not a sharp spike. The density argument had problems too. If interstellar space contained enough objects to explain current detections, previous surveys should have found some. The non-detection history placed upper limits on density that current observations exceeded by factors of 100. That left the third option, which no one wanted to consider seriously. The idea that interstellar objects might be directed rather than random violated fundamental assumptions. It suggested intention where we expected chaos. Dr. Rodriguez examined approach vectors. While not perfectly aligned, the 3 confirmed visitors came from the same celestial hemisphere. The probability of random clustering was about 15%. Not impossible, but combined with timing and detection rates, the coincidences multiplied. The characteristics showed disturbing progression. Oumuamua was inert but accelerating. Borisov was active but conventional. 3I/ATLAS was active and impossible. Each visitor was stranger than the last, as if testing our observation capabilities. Some proposed a common origin event. Perhaps a stellar collision or planetary system disruption had sent debris our way. But the chemistry differences argued against single source. The velocities didn't trace back to any common point. The interstellar meteor question added complexity. Since 2014, several fireballs showed speeds suggesting interstellar origin. If confirmed, it meant smaller objects arrived frequently. We were swimming in interstellar debris without knowing it. Dr. Rodriguez's most speculative calculation was sobering. If arrival rates continued increasing at current pace, we'd detect dozens of interstellar objects by 2030. Our solar system would become a cosmic thoroughfare. The implications for planetary defense were staggering. The sample size problem frustrated everyone. 3 objects were too few for statistics, but too many for coincidence. We needed dozens to establish patterns, but each new detection raised more questions than answers. As December approached, observers worldwide watched for new arrivals. Were these 3 visitors isolated events or the vanguard of something larger? The answer might reshape our understanding of our cosmic neighborhood. The extended family hypothesis suggested 3I/ATLAS wasn't alone, wasn't unique, wasn't even unusual. It was simply the most recent member of a population we were just beginning to discover. A population that shouldn't exist in such numbers. The energy budget of 3I/ATLAS defied basic thermodynamics. The numbers were clear, verified by multiple teams, and impossible. Something was powering this object beyond what the sun could provide. Dr. Kevin Thompson at Caltech ran the calculations obsessively. The observed gas production rate required 40 megawatts of continuous power. Solar heating at 3I/ATLAS's distance provided 4 megawatts maximum. The deficit was an order of magnitude, far beyond measurement uncertainty. Where could this energy originate? Radioactive decay was the obvious answer. Uranium, thorium, potassium-40 all generate heat through nuclear decay. But the required concentrations would make 3I/ATLAS more radioactive than nuclear reactor fuel. The gamma-ray signature would be obvious. None was detected. Chemical energy offered another possibility. Exothermic reactions could release heat, driving sublimation. But which reactions? At -120 degrees Celsius, most chemistry stops. The few reactions possible at such temperatures couldn't generate megawatts of power for months. Dr. Thompson considered exotic physics. Could 3I/ATLAS contain antimatter, annihilating slowly to produce energy? The power output matched, but antimatter would produce distinctive gamma rays. Observatories detected nothing unusual in high-energy bands. Magnetic field interactions were proposed. If 3I/ATLAS carried strong permanent magnets, interaction with solar wind could generate heat through induction. But the required field strengths exceeded anything possible with known materials. And magnetometers detected no unusual fields. The power consistency troubled analysts. Natural energy sources fluctuate. Radioactive decay is random. Chemical reactions vary with temperature. Solar heating changes with distance and orientation. But 3I/ATLAS maintained steady power output regardless of conditions. Some suggested internal heat reservoirs. Perhaps 3I/ATLAS stored thermal energy in phase change materials, releasing it slowly. But the total energy required exceeded what any known material could store in the available volume. Dr. Thompson's team examined electrical possibilities. Triboelectric charging from dust impacts could generate voltage differences. Photoelectric effects might contribute. But these mechanisms produced milliwatts, not megawatts. The scale was wrong by factors of millions. Tidal heating seemed impossible for such a small object. Tidal forces require size and close approaches to massive bodies. 3I/ATLAS was too small, too far from any planet. The calculations yielded essentially zero tidal energy. The quantum vacuum energy hypothesis was desperate speculation. Could 3I/ATLAS somehow extract zero-point energy from space itself? The physics was theoretical at best, fiction at worst. But conventional explanations had all failed. Biological processes were considered and dismissed. Even the most efficient life forms couldn't generate such power densities. And biology couldn't survive the radiation exposure of interstellar travel. The idea was fantasy. The power problem connected to other anomalies. The non-rotation might indicate internal gyroscopes requiring energy. The missing water might result from power-intensive chemistry. The enormous gas cloud definitely needed continuous energy input. Dr. Thompson reached an uncomfortable conclusion. 3I/ATLAS possessed an energy source we couldn't identify. Not nuclear, not chemical, not solar. Something else. The implications were profound and troubling. As December began, the power mystery deepened. Post-perihelion observations showed no decrease in energy output despite increasing solar distance. Whatever powered 3I/ATLAS wasn't weakening. If anything, it seemed to be intensifying. The energy requirements weren't just anomalous, they were impossible with known physics. Yet the observations were unambiguous. 3I/ATLAS was powered by something beyond our understanding. December 1st, 2025, 4:47 a.m. Hawaii Standard Time. The Subaru telescope captured the first post-conjunction image of 3I/ATLAS. What emerged from behind the sun's glare shattered remaining hopes for conventional explanations. Dr. Jennifer Kim coordinated the global observation campaign. Telescopes worldwide had been waiting weeks for this moment. The first images were supposed to answer questions. Instead, they created new mysteries that challenged basic assumptions about matter and energy. 3I/ATLAS had changed, not subtly, dramatically. The nucleus appeared 30% brighter than pre-conjunction predictions. The gas cloud had expanded to 400,000 kilometers, larger than ever observed. Most disturbing, the chemistry had shifted in ways that shouldn't be possible. New spectral lines appeared that hadn't existed before. Not faint traces, but strong emissions indicating molecular species absent in October. Cyanogen, never detected before conjunction, now dominated parts of the spectrum. Where had it come from? How had it formed? The CO2 to water ratio, that impossible 8:1 signature, had changed to 12 to 1. Water had become even scarcer, while CO2 production increased. This violated thermodynamic models that predicted the opposite trend. Higher temperatures should release more water, not less. Dr. Kim's team worked around the clock analyzing data. Each measurement was verified by multiple observatories. The changes were real, consistent, and impossible to explain through normal perihelion passage. The morphology had evolved too. Pre-conjunction, 3I/ATLAS showed a roughly spherical coma. Now structures appeared. Jets, fans, and shells of gas created complex patterns. But these features didn't match typical comet behavior. They were too stable, too geometric, too regular. Color had shifted toward blue, indicating smaller dust particles or different composition. But the dust production rate seemed unchanged. How could particle size change without affecting production? The physics didn't connect. Temperature measurements yielded more confusion. The nucleus was cooler than expected. Despite recent perihelion passage, it should be radiating stored heat. Instead, surface temperature had dropped 20 degrees below predictions. Heat was disappearing somewhere. The rotation mystery deepened. Still no periodic variations, despite dramatic activity changes. Whatever prevented rotation before had survived perihelion's violent heating. The stabilization mechanism, whatever it was, remained active. Radio observations detected something new. Coherent emissions at specific frequencies. Not quite artificial signals, but more organized than natural thermal radiation. The patterns suggested resonance phenomena. But resonance with what? Dr. Kim discovered the most troubling change through careful photometry. 3. I/ATLAS showed rapid brightness variations on timescales of minutes. Not rotation, not outgassing pulses. Something else. The variations followed no pattern anyone could identify. Polarimetry revealed another anomaly. Light from 3 I/ATLAS was partially polarized in ways suggesting aligned particles or organized structures. Natural comets show random polarization from chaotic dust. This was different. Organized. Structured. The European team confirmed changes in orbital parameters. Tiny but measurable accelerations had occurred during conjunction. Not from outgassing. The direction was wrong for that. Something had pushed 3 I/ATLAS during perihelion, altering its trajectory slightly. As December progressed, each observation added to the growing catalogue of impossibilities. 3 I/ATLAS hadn't just survived perihelion. It had transformed in ways that challenged fundamental physics. The December observations were supposed to provide closure, final answers before 3 I/ATLAS faded into distance. Instead, they revealed that our 6-week blindness had hidden crucial events. Something had happened during conjunction. Something that changed everything. December 5th, 2025. High-resolution imaging from the Keck Observatory revealed what astronomers had feared since November. 3 I/ATLAS showed signs of potential fragmentation. Not the violent breakup of a dying comet, but something more subtle and far more troubling. Dr. Michael led the analysis team. The images showed multiple brightness centers within the coma. Not the single compact nucleus observed before conjunction, but 3 distinct concentrations of material. The implications were staggering and dangerous. If 3 I/ATLAS was fragmenting, the debris could spread across a vast volume of space. Individual fragments would be harder to track, easier to lose. Our chance to study this mysterious visitor might literally be breaking apart before our eyes. But the fragmentation pattern defied conventional models. Normal comet breakups are violent, explosive events. Thermal stress or rotational forces overcome structural integrity. Fragments fly apart at hundreds of meters per second. This was different. The 3 components maintained precise spacing, moving in formation like a cosmic convoy. Separation distances remained constant over days of observation. The fragments weren't diverging. They were traveling together, maintaining relative positions with mechanical precision. Dr. Michael's calculations revealed the impossible. The gravitational attraction between fragments was too weak to maintain such spacing. Solar radiation pressure should push them apart. Solar wind should scatter them. Yet they remained in formation, defying forces that should disperse them. Spectroscopic analysis added confusion. Each fragment showed slightly different chemistry. Component A was CO2 rich. Component B showed water signatures previously missing. Component C displayed organic molecules absent from other fragments. It was like 3I/ATLAS had sorted itself by composition. The size estimates were troubling. Each fragment appeared comparable to the original nucleus lower limit. Combined, they exceeded the maximum pre-conjunction size estimates. Either 3I/ATLAS had been larger than believed, or mass was appearing from somewhere. Formation flying suggested active control. But by what mechanism? No natural process could maintain such precise spacing against dispersive forces. The fragments acted like they were connected by invisible threads or following programmed trajectories. Dr. Michael examined breakup triggers. Perihelion thermal stress was the obvious cause, but the timing was wrong. Fragmentation should occur during maximum heating, not a week later. The delayed response suggested a process more complex than simple thermal fracturing. The fragment designation itself became controversial. Were these separate objects or parts of a distributed whole? The boundaries between components were fuzzy, connected by streams of gas and dust. It looked less like breakup and more like deployment. Radar observations from Goldstone provided crucial data. The radar returns showed solid cores for each fragment, not rubble piles or dust clouds. These were substantial objects, each capable of independent activity. But their coordinated behavior suggested anything but independence. The orbital mechanics were precisely synchronized. As 3I/ATLAS moved through space, the fragments rotated around their common center of mass. But the rotation was too perfect, maintaining orientations that maximize solar exposure for each component equally. Dr. Michael's team modeled thousands of fragmentation scenarios. None reproduced observations. Natural physics couldn't explain the formation flying. But the alternative, active station keeping, implied capabilities that transformed 3I/ATLAS from curiosity to concern. NASA's Planetary Defense Office upgraded their monitoring. While 3I/ATLAS posed no impact threat, the fragmentation introduced new variables. 3 objects were harder to track than 1. If further fragmentation occurred, we might lose track entirely. As December progressed, the fragments remained locked in formation. Whatever process had separated them was complete. They traveled as a unit, 3 parts of something that was never really one. The decision to actively signal 3I/ATLAS came after weeks of debate. On December 10, 2025, humanity deliberately transmitted radio signals toward an interstellar visitor for the first time. The results were immediate, impossible, and terrifying. Dr. Sarah Martinez led the transmission team at Arecibo's successor facility. The protocol was conservative. Prime numbers in binary, the universal mathematical language any intelligence should recognize. The signal lasted 90 seconds at 1.42 GHz near the hydrogen line frequency. Light travel time to 3I/ATLAS was 12 minutes each way. The team expected to wait 24 minutes for any possible response. They waited only 3 minutes. The reply came before their signal could have reached the target. The response was unmistakable. 3I/ATLAS's radio emissions, previously steady, pulsed in the exact prime number sequence Earth had transmitted. But the timing was impossible. The visitor had responded before receiving the message. Dr. Martinez verified equipment, checked for errors, examined alternative explanations. The timestamps were accurate. Multiple observatories confirmed the sequence. 3. I/ATLAS had somehow anticipated Earth's transmission and responded preemptively. The implications shattered comfortable assumptions. Either 3 I/ATLAS could predict human actions, or it was monitoring Earth communications in real time through methods that bypassed light speed limits. Neither option belonged in conventional physics. A second transmission was prepared, this time using different mathematical constants. Pi, expressed in binary to 20 digits. The signal was sent at 14:30 UTC. Again, 3 I/ATLAS responded before the signal arrived, broadcasting pi to 30 digits. The extended precision was deliberate. Not only did 3 I/ATLAS know Earth's transmission content in advance, it was demonstrating superior knowledge. The extra digits of pi were correct, like a teacher correcting a student's homework. Radio telescopes worldwide joined the effort. Coordinated observations revealed 3 I/ATLAS was transmitting on multiple frequencies simultaneously. Each frequency carried different information. Mathematical sequences, physical constants, and patterns that resembled encoding schemes. Dr. Martinez's team attempted more complex communication. They transmitted a bitmap image, 23 by 73 pixels showing a hydrogen atom. 3 I/ATLAS responded with the same image at higher resolution, adding electron orbital details Earth's simple diagram omitted. The power requirements for 3 I/ATLAS's transmissions exceeded anything a comet-sized object should generate. The signals were strong enough to detect across the solar system. Whatever powered the visitor wasn't just maintaining activity, it was broadcasting. Pattern analysis revealed structure in 3 I/ATLAS's emissions. Not random pulses, but organized data packets. Headers, error correction, formatting that suggested sophisticated communication protocols. Someone or something had designed these signals for interpretation. The fragmented nature of 3 I/ATLAS added complexity. Each component transmitted different signals on different frequencies. Combined, they created interference patterns that encoded additional information. It was communication through choreographed electromagnetic dance. Dr. Martinez discovered frequency hopping in the signals. 3 I/ATLAS cycled through specific frequencies in patterns that matched Earth's radio telescope capabilities. It knew which frequencies we monitored and tailored its transmissions accordingly. SETI protocols activated worldwide. If 3 I/ATLAS was attempting communication, humanity needed coordinated response strategies. But the visitor's apparent precognition made planning nearly impossible. How do you communicate with something that knows your messages before you send them? As December progressed, 3 I/ATLAS's signals grew more complex. Mathematical concepts gave way to physics equations, chemical formulas, and patterns that might represent biological information. It was teaching us, or testing us, or something else entirely. The communication attempts had succeeded too well. We had made contact. But contact with what? December 15th, 2025. Every 24 hours brought observations that contradicted the previous day's understanding. 3 I/ATLAS had become astronomy's daily crisis, each dataset invalidating yesterday's theories while creating tomorrow's impossibilities. This morning's spectroscopy from JWST showed water vapor, strong, clear signals at 2.7 microns wavelength. The water mystery was solved. This afternoon's follow-up found no water at all. The morning's signal had vanished completely. Both observations were verified, calibrated, real. Dr. Alan Foster coordinated the rapid response teams. His job had become managing scientific chaos. Each observatory reported anomalies that shouldn't exist. The data was accurate. Reality was apparently unstable. Brightness measurements told their own paradoxical story. Palomar Observatory recorded magnitude 11.3 at 2 a.m. Subaru measured 10.8 at 2:15 a.m. Keck found 11.7 at 2:30 a.m. 3 telescopes, same object, wildly different brightnesses in minutes. Instrumental error was ruled out. The fragmentation count kept changing. December 14th showed 3 components. December 15th morning revealed 5. By evening, back to 3. High-resolution imaging confirmed each count. Objects were appearing and disappearing, or merging and splitting, faster than physics allowed. Chemical composition had become meaningless. Each spectrum showed different molecules. Morning observations detected ammonia. Afternoon found methane. Evening revealed silicon compounds. The chemistry was reshuffling in real time, like a cosmic slot machine. Dr. Foster's database grew exponentially. Terabytes of contradictory data accumulated daily. Machine learning algorithms designed to find patterns crashed, unable to reconcile observations. The data wasn't just anomalous. It was internally inconsistent. Temperature readings defied thermodynamics. Infrared telescopes measured the nucleus at minus 110 degrees Celsius. 30 minutes later, minus 140 degrees Celsius. Then, minus 95 degrees Celsius. The temperature swung by dozens of degrees without cause. No heat source, no cooling mechanism. Just change. Polarization measurements were impossibly variable. Light from 3 I/ATLAS showed linear polarization, then circular, then unpolarized, cycling through states in hours. The dust properties required to produce such changes couldn't physically exist. Radio emissions had evolved from structured to chaotic. The clear mathematical patterns of early December dissolved into noise, but not random noise. Statistical analysis suggested information content, but no decoding scheme worked. It was meaning without interpretation. Dr. Foster discovered correlations that shouldn't exist. 3 I/ATLAS brightened when Mars was visible from Earth. It dimmed during lunar eclipses. Chemical signatures changed with Earth's weather patterns. These correlations were statistically significant, but physically impossible. The velocity showed micro-variations, not the smooth deceleration of solar escape, but stutters. Speed changes of meters per second, lasting minutes, then reversing. As if 3 I/ATLAS was testing different velocities, sampling possibilities. Size estimates had become jokes. Each measurement method gave different results that changed daily. Radar said 2 kilometers. Optical suggested 8 kilometers. Thermal indicated 500 meters. All measurements were correct. None agreed. International cooperation was breaking down. Teams couldn't agree on basic observations. Data that supported one theory contradicted another. Peer review became impossible when peers saw different realities. Dr. Foster's evening briefing was stark. We have perfect instruments observing an imperfect reality. Either 3 I/ATLAS violates physics in ways we can't comprehend, or observation itself has become unreliable. The growing database wasn't building understanding. It was documenting ignorance. Each byte of data added confusion rather than clarity. Tomorrow would bring new observations that would contradict today's, which had already contradicted yesterday's. 3 I/ATLAS hadn't just defied explanation. It had made explanation impossible. The International Astronomical Union meeting on December 18, 2025, was supposed to build consensus about 3 I/ATLAS. Instead, it revealed a scientific community fracturing along lines nobody had anticipated. The division wasn't between disciplines or nationalities, but between those who still believed in conventional explanation and those who had abandoned it. Dr. Robert Hayes led the conservative faction. His presentation was meticulous, showing how measurement uncertainties, instrumental artifacts, and observational biases could explain some anomalies. Not all, he admitted, but enough to maintain scientific orthodoxy. We're seeing selection effects, Hayes argued. We notice the strange measurements and ignore the normal ones. 3I/ATLAS is unusual, yes, but not impossible. Give us time. Physics will prevail. Dr. Avi Loeb represented the opposite view. His slides showed the accumulating impossibilities. Energy budgets that didn't balance, chemistry that shouldn't exist, behaviors that violated thermodynamics. His conclusion was stark. Conventional physics had failed. We're like 19th century physicists trying to explain radioactivity with classical mechanics, Loeb stated. 3I/ATLAS operates according to principles we haven't discovered. Clinging to failed models isn't skepticism, it's denial. The audience was split. Younger researchers, less invested in established theories, showed openness to exotic explanations. Senior astronomers, careers built on conventional physics, demanded more evidence before abandoning proven frameworks. Dr. Elena Vasquez proposed middle ground. Perhaps 3I/ATLAS represents natural phenomena at extreme conditions we've never observed. Not new physics, but physics pushed to limits we didn't know existed. The data presentation became contentious. Each team's observations contradicted others. European astronomers showed steady brightness. American telescopes recorded variations. Asian observatories found patterns neither group detected. "We're not even seeing the same object," shouted one frustrated researcher. The comment was meant as hyperbole. The silence that followed suggested others were considering it literally. Funding agencies attended, evaluating resource allocation. NASA representatives looked concerned. ESA delegates took notes. Private foundations reconsidered their investments. If scientists couldn't agree on basic observations, how could they justify billion-dollar research programs? The peer review crisis was discussed openly. 3 papers on 3I/ATLAS had been submitted to Nature. Reviewers couldn't agree on any of them. One paper's observations were called impossible by referees who had different data. The journal editors were paralyzed. Dr. Hayes presented error analysis showing how some anomalies fell within measurement uncertainty. But Dr. Loeb countered with statistical arguments proving the anomalies were significant. Both were right. The mathematics supported contradictory conclusions. The theoretical physics community had begun paying attention. String theorists suggested extra dimensions. Quantum mechanicists proposed macro-scale superposition. Cosmologists wondered about dark matter interactions. None of these explanations fit all observations. Some researchers had stopped publishing. Why submit papers that would be rejected for contradicting other papers that would also be rejected? The normal scientific process had broken down. The meeting's final vote was telling. A resolution to classify 3I/ATLAS as anomalous pending further investigation passed narrowly. But the defeated resolution, to acknowledge phenomena beyond current scientific understanding, had received 45% support. As the meeting concluded, private conversations revealed the real divide. Half the astronomers were excited by the mystery. Half were terrified by it. Some saw career-defining discovery. Others saw career-ending confusion. The professional community wasn't just divided on interpretation. They were divided on whether interpretation was even possible. By December 20th, 2025, the list of absent phenomena had become as troubling as the anomalies. 3I/ATLAS wasn't just showing impossible features. It was missing fundamental characteristics that defined every comet ever studied. Dr. Jennifer Park compiled the Absence Catalogue. Her document read like an inventory of missing evidence at a crime scene. Each absence violated decades of cometary science. Together, they suggested 3I/ATLAS wasn't a comet at all. First absence, the dust trail. Every active comet leaves a trail of particles along its orbit. These particles spread over millions of kilometers, creating meteor streams when planets pass through. 3I/ATLAS left nothing. Space behind it was as empty as space ahead. The non-detection wasn't from lack of trying. Infrared telescopes searched for thermal signatures of dust. Radar looked for particle reflections. Wide-field cameras hunted for scattered light. The trail didn't exist. Second absence. Ion tail. Solar wind should strip ions from any comet's coma, creating a straight tail pointing away from the sun. 3I/ATLAS showed no ion tail. Magnetometers detected no charged particle streams. It was like solar wind didn't affect it. Third absence, seasonal chemistry. As comets warm approaching the sun, different ices sublimate at different temperatures. First CO2, then CO, then water. The sequence is predictable. 3I/ATLAS showed no sequence. All volatiles appeared simultaneously, or not at all. Fourth absence, asymmetric outgassing. Comet nuclei have varied compositions. Some regions are ice-rich, others dust-covered. This creates jets and fans as different areas activate. 3I/ATLAS showed perfectly symmetric emission despite dramatic activity. Dr. Park discovered subtler absences. No hydroxyl variation with solar rotation. No correlation between gas production and heliocentric distance. No spectral lines from common minerals like olivine or pyroxene. The missing sodium was particularly puzzling. Even tiny amounts of sodium produce bright emission lines that dominate comet spectra. Every comet shows sodium. 3I/ATLAS showed none. It was like finding ocean water without salt. Nitrogen compounds were inexplicably absent. N2, NH3, HCN, molecules common in comets, essential for understanding formation temperatures. 3I/ATLAS showed no nitrogen despite perfect conditions for detection. The absence of periodic phenomena troubled physicists. No orbital precession from solar torques. No thermal lag between heating and outgassing. No tidal effects from planetary encounters. 3I/ATLAS moved through the solar system untouched by forces that affected everything else. Dr. Park found missing correlations. Gas production didn't match solar flux. Brightness didn't correlate with phase angle. Temperature didn't follow distance. Every expected relationship was absent. The non-detection of fragments was impossible. Active comets shed house-sized chunks regularly. These should be visible as companion objects. Searches found nothing. 3I/ATLAS remained solitary despite massive activity. Fluorescence was absent. Sunlight should excite molecules in the coma, causing them to glow at specific wavelengths. This fluorescence is how we identify cometary molecules. 3I/ATLAS showed direct emission but no fluorescence. The missing phenomena formed their own pattern. Everything absent was something that would constrain 3I/ATLAS's nature. Dust trails would reveal mass loss rates. Ion tails would indicate composition. The absences seemed selective, designed. As December progressed, Dr. Park's list grew. Each new observation added missing features. We were learning more about what 3I/ATLAS wasn't than what it was. The absences had become presences. The missing evidence was itself evidence of something beyond conventional understanding. December 25th, 2025, Christmas Day. While Earth celebrated, 3I/ATLAS continued its relentless journey away from the sun. In 6 weeks, it would fade beyond our best telescope's ability to detect. The countdown to ignorance had begun. Dr. Michael Thompson coordinated the final observation campaign. Every telescope capable of tracking 3I/ATLAS was assigned specific tasks. There was no time for redundancy. Each observation had to count. The mystery would soon pass beyond our reach forever. Current distance, 2.8 astronomical units, and increasing by 5 million kilometers daily. Brightness, magnitude 13.2 and fading by 0.1 magnitudes per week. At current rates, 3I/ATLAS would drop below detection threshold by February 10th, 2026. The observation schedule was ruthless. JWST had 72 hours allocated, its maximum possible given other commitments. Hubble received 48 hours. Ground observatories worked in shifts, tracking 3I/ATLAS whenever weather permitted. Every photon was precious. Priority lists were brutal. Chemical composition topped essential observations. Fragmentation monitoring was second. Communication attempts were controversial third. Everything else was sacrificed. Career-defining research proposals were rejected for 5-minute glimpses of 3I/ATLAS. Dr. Thompson's team developed contingency protocols. If 3I/ATLAS brightened unexpectedly, all telescopes would converge. If it fragmented further, tracking would focus on the largest piece. If communication patterns emerged, SETI protocols would activate. Every scenario was planned except the most likely. 3I/ATLAS fading without explanation. The data pipeline was optimized for speed over perfection. Raw observations were shared instantly, analysis would come later. The normal months-long publication process was abandoned. Papers were posted to preprint servers within hours of observation. Peer review would have to wait. Some researchers were already writing retrospectives, papers titled What We Learned from 3I/ATLAS and Lessons for Future Interstellar Visitors. The use of past tense was premature, but psychologically revealing. The community was preparing for loss. Dr. Thompson fought against fatalism. We have 6 weeks. That's 1,000 hours of potential observation. Oumuamua gave us 11 days. We're fortunate, not cursed. But the pressure was crushing. Each failed observation meant permanent ignorance. Every cloudy night was lost forever. Equipment failures became catastrophes. A power outage at Keck cost 3 hours of irreplaceable data. The fragmentation complicated everything. 3 objects required triple the telescope time. If they separated further, we might lose some entirely. The countdown applied to each fragment independently, and smaller pieces would fade first. Radio monitoring continued desperately. If 3I/ATLAS was attempting communication, we had weeks to decode it. After that, silence forever. The possibility that we might miss a message from another civilization drove round-the-clock analysis. Dr. Thompson's daily briefings had developed a grim rhythm. Distance update, brightness measurement, days remaining. Each number was precise, clinical, final. The countdown was inexorable. January 1st, 2026 would mark a psychological threshold. A new year with 3I/ATLAS still visible but fading. By month's end, only the largest telescopes would detect it. By February, nothing. The European Space Agency proposed a desperate mission: launch a CubeSat on a suborbital trajectory with a small telescope. Above Earth's atmosphere, it could observe for precious extra hours. The proposal was technically feasible, financially impossible. As December ended, resignation was settling over the community. We had learned enough to know we understood nothing. 3I/ATLAS would leave us with questions that might never be answered. The countdown continued. 5 weeks, 35 days, 840 hours. Each number smaller than the last, measuring our approach to permanent mystery. December 28th, 2025. Behind closed doors at NASA headquarters, a different kind of meeting was taking place. Not about trajectories or chemistry, but about implications. What if the growing anomalies pointed to conclusions that challenged more than just physics? Dr. Patricia Williams, NASA's deputy administrator, had convened the session. Attendees included military advisors, philosophers of science, and psychologists specializing in social response to paradigm shifts. The discussion was classified, though leaks would emerge months later. We need to consider all possibilities, Williams began, including those that might fundamentally alter humanity's understanding of its place in the universe. The briefing documents outlined scenarios. What if 3I/ATLAS demonstrated technology? What if its anomalies indicated physics beyond human comprehension? What if it was observing us as much as we observed it? Each scenario had protocols that read like science fiction. The military advisor was direct. If this object shows technological signatures, it demonstrates capabilities we can't match. The national security implications are staggering. The room understood. Superiority in space had geopolitical consequences. The psychologist presented social impact models. Previous paradigm shifts, like discovering Earth orbited the Sun, had triggered social upheaval, but those were abstract concepts. 3I/ATLAS was visible, immediate, undeniable. Public reaction to certain discoveries could destabilize society. We're not prepared for answers that challenge human uniqueness, she stated. Our entire cultural framework assumes we're alone, or at least first. What happens to that framework if we're neither? Dr. Williams revealed that certain observations were being withheld pending analysis, not classified exactly, but delayed. Data that might be misinterpreted, causing panic before understanding. The scientific community was already fracturing. Public fracturing could be worse. The philosopher raised ethical concerns. Did humanity have the right to make contact with something we didn't understand? If 3I/ATLAS was more than a comet, our observations might be interactions. Were we ready for the responsibilities that implied? Discussion turned to information management. How much uncertainty could the public handle? Should anomalies be presented as mysteries or minimized as measurement errors? The balance between transparency and stability was delicate. The contingency protocols were sobering. If certain thresholds were met, pre-written statements would be released. Government agencies would coordinate messaging. International bodies would convene. The machinery for managing species-level revelation was already in motion. What thresholds? Someone asked. Unambiguous technological signature, directed communication, evidence of observation or surveillance. The list continued. Each item represented a crossing point beyond which secrecy became impossible. Dr. Williams addressed the elephant in the room. Some of you believe we've already crossed those thresholds. The precognitive radio response, the formation flying, the impossible chemistry. Any single anomaly might be explained. Together, they suggest something beyond conventional science. The meeting concluded without resolution. Decisions were postponed, hoping additional data would clarify rather than complicate. But everyone understood the subtext. We were preparing for the possibility that 3I/ATLAS might force humanity to confront truths we weren't ready to accept. As December ended, these preparations intensified. Crisis communication teams were assembled. International coordination channels were established. Philosophical and theological advisors were consulted. We were preparing for answers. But more importantly, we were preparing for answers we didn't want to hear. December 31st, 2025, 11:47 p.m. In 13 minutes, the world would celebrate a new year. In 13 minutes, the Atacama Large Millimeter Array would begin its final high-resolution observation of 3I/ATLAS for 2025. Tomorrow's data would either break through or break down our understanding completely. Dr. Sarah sat at the control console, watching the atomic clock tick toward midnight. ALMA's 66 radio dishes were perfectly synchronized, ready to function as a single massive telescope. Tonight's observation might be their last chance to detect the molecular emissions that could explain everything. The target list was specific: complex organic molecules that might indicate biological processes, phosphine that could suggest exotic chemistry, technosignatures, patterns that nature couldn't create. Each detection would rewrite textbooks. Each non-detection would deepen mystery. Around the world, other astronomers were preparing their own final observations of the year. In Hawaii, Keck Observatory would attempt to resolve the fragments one more time. In space, JWST would measure isotope ratios with unprecedented precision. Every telescope that could see 3I/ATLAS would try. Dr. Sarah reflected on 6 months of impossible observations, the journey from puzzling discovery to complete bewilderment. Each answered question had spawned 10 new ones. We knew less now than when we started, despite thousands of hours of observation. The countdown reached 0. 2026 began. ALMA's dishes moved in perfect synchronization, tracking 3I/ATLAS across the sky. Data began flowing, spectra that might contain answers or might contain more questions. Initial results were immediate and impossible. Strong emission lines where none should exist. Molecular signatures that required temperatures and pressures not present in space. Chemistry that suggested processes we didn't understand. But embedded in the noise was something else, a pattern in the molecular emissions. Not random, not natural, structured in ways that suggested information encoding. As if 3I/ATLAS was using chemistry itself as a communication medium. Dr. Sarah's hands trembled as she verified the data. This wasn't like the radio signals. This was more fundamental. Information encoded at the molecular level, using the universe's basic building blocks as an alphabet. The implications were staggering. If confirmed, this would mean 3I/ATLAS wasn't just unusual or anomalous. It was actively communicating through methods we'd never imagined. Every molecule a message, every spectrum a sentence. Tomorrow, January 1st, 2026, these observations would be analyzed, verified, debated. Teams worldwide would scramble to confirm or refute. The scientific community would either unite in recognition of paradigm shift or fragment further in disagreement. But tonight, in the first minutes of the new year, Dr. Sarah sat alone with data that might change everything. 3I/ATLAS continued its journey outward, carrying secrets we'd only begun to glimpse. In 5 weeks, it would fade beyond detection. Whatever truths it carried would be lost, unless tomorrow's observation revealed the key, unless the molecular message could be decoded, unless we could understand what 3I/ATLAS had been trying to tell us all along. The radio dishes continued tracking through the night, data accumulated, patterns emerged and dissolved, the mystery deepened with each measurement. 3I/ATLAS wasn't becoming less terrifying as we studied it. It was becoming more terrifying because we were beginning to understand that we understood nothing. Tomorrow would bring new observations, new contradictions, new impossibilities. The terror wasn't in what 3I/ATLAS might do. The terror was in what it meant for everything we thought we knew. The truth was out there, racing away at 130,000 miles per hour.